Okay, so here's something you've probably wondered about. Your Wi-Fi signal, it just sails right through the walls in your house, no problem at all. But then you grab a flashlight, shine it at the same exact wall, and, well, nothing happens. It's just a wall. So why is that? Let's get into it. And this is the real head scratcher. Because here's the thing. On a really basic fundamental level, the radio waves from your Wi-Fi and the light from your flashlight, they're basically the same stuff. They're both electromagnetic waves. So what gives? How can one get a free pass to go right through a wall while the other just gets stopped in its tracks? That's the puzzle we're going to piece together. All right, so to figure this out, we've got to start with what makes these two things the same. Before we get into what makes them different, let's talk about their shared family identity. So what in the world is an electromagnetic wave? Well, you can think of it as pure energy that's kind of surfing through space, and it's riding on these electric and magnetic fields that it actually creates for itself as it goes. Super cool, right? This means it doesn't need anything like air or water to travel through. It can just go. That's exactly how sunlight gets all the way here from the sun through the total vacuum of space. And look at this. This really gets to the heart of the problem, doesn't it? Visible light, radio waves, they're both officially in the same club. They're siblings. So if they're made of the exact same fundamental stuff, the answer to why they act so differently has to be something they don't share. Okay, now we're getting somewhere. This is our first big clue, the thing that starts to pull the whole thread. And it all comes down to one really big difference, their size, or as a physicist would call it, their wavelength. So check this out. This is like the whole family photo. The electromagnetic spectrum is this huge range from these absolutely massive radio waves on one end all the way down to these teeny tiny gamma rays on the other. Now, find our two guys. See? Radio waves are the giants of the family. And then way, way, way down the line, you find visible light squeezed into this incredibly narrow little slice of the whole thing. And this is the key takeaway here. The difference in size is just massive. I mean, think about it. A single radio wave could be the size of a building or even bigger, but a light wave? It's smaller than a single bacterium. It's just unbelievably tiny. And that huge difference in size, that's the first key to solving this whole thing. But, size isn't everything. It's only half the story. The second piece of the puzzle is tied directly to that size, to that wavelength. And that's all about energy, the amount of energy each of these waves is packing. Okay, so let's break this down. Every wave is made up of these little energy packets called photons. Now, if you have a really long wavelength, like a radio wave, that means you have low energy photons. They're just kind of weak. They don't have enough oomph to really bother the electrons inside the atoms of a wall. But the photons in visible light, oh, they are in the Goldilocks zone. Not too much energy, not too little. They have the perfect amount of energy to get absorbed by those electrons. And that absorption is what stops the light dead in its tracks. All right, we've got our clues. Clue number 1, a huge difference in size or wavelength. Clue number 2, a matching difference in energy. So let's put it all together and crack this case. And here it is, the big answer. For a radio wave, a wall is basically invisible. It's like trying to catch a beach ball with a fishnet. The wave is so enormous compared to the atoms in the wall, it just sails right on through. It doesn't even see them. Plus, its energy is way too low to get absorbed. But for visible light, that same wall is like a super dense forest. The light waves are so tiny, they're the right size to constantly bump into all the atoms. And they have that just right energy level to get completely absorbed. The light stops, and its energy just turns into a little bit of heat. So let's just walk through it one more time. You've got both waves heading for the wall. The radio wave, because it's so big and low energy, just cruises right on through like the wall isn't even there. But the light wave, because it's so small and has that perfect amount of energy, it gets napped, it's absorbed, and its journey is over. So this isn't just a trick that radio waves can do. Now that we understand the secrets, long wavelength, low energy, we can see how other members of the electromagnetic family have this same kind of see-through superpower. Yeah, take microwaves. They're really just a shorter kind of radio wave. That's exactly why your Wi-Fi and Bluetooth signals work so well. They're microwaves, and they have no problem passing through most materials in your house. And it's the same for some types of infrared light. That's how thermal cameras can sometimes see a heat signature right through a thin wall. It all comes back to that winning combo, long wavelength and low energy. So we figured it out.
Mystery solved, but it leaves you with a really cool thing to think about, right? Our entire experience of the world is filtered through this one tiny little slice of the spectrum we call visible light. It's a world where walls are solid, but just imagine, what if your eyes could see in radio waves? Your house would look transparent, you'd see this invisible storm of signals from phones and Wi-Fi all around you, the night sky, the whole universe would look totally alien. It just makes you wonder how much of reality is happening all around us, all the time, completely unseen.